At the beginning of Chapter 4, we mentioned that we were going to be looking at four basic ways that circuits are constructed. And the first method we're going to be looking at, and the most basic, is series circuits. As a technician, it is important to understand series circuits. A series circuit is characterized as having only a single path for current flow. And so here we have a source of EMF, and we have a component connected. As down here we have a voltage source, and we have a component connected, in this case a light bulb. But in both these cases there is only one path for current flow. There's only one way that current can flow. There's no alternative paths. There is only one path, and that makes this a series circuit. Series components are connected such that only a single path exists for current flow without encountering any branches in the circuit. If every electron that leaves the negative terminal of the power source has only one path for current, then the circuit is a series circuit. And so you see in this case here, the negative pole, or the negative side of this, negative to positive, every electron that passes only has one possible path for current, and so we will call that a series circuit. In a series circuit, since there is only one path for current flow, each component of the circuit has the same current flowing through it as flows through the entire circuit. That's an important aspect of a series circuit. Since there is only one path for current flow, then the same current that goes through R2, R3, and R1. It is the same amount of current. It's kind of like when we talked about that hydraulic system. The hydraulic system has a pump, and if it's just a single, if it's a loop, then the same amount of fluid that goes through this, and goes through this. And that was the analogy to the hydraulic pump that we talked about in previous lessons. Okay, now this particular circuit here, I have a question. Are the above series circuits? Well, this is obviously a series circuit. But in this case, we start out with our voltage source. Current comes in. It goes through, all the current from the source goes through R2. But now we have what we're calling a branching. And this is going to be a parallel circuit. So the circuit is going to go through this branch of resistors here, and then come back through this circuit. So this is no longer truly a series circuit. It is a series circuit, but it has a parallel branch over here. And later in this chapter we'll be looking at parallel circuits. Series circuits. This is a section called intuitive relationships. And intuitive relationships are things that they just kind of make sense. And in series circuits, there are some things that are just intuitive about a series circuit. In your text, we'll give a little bit of discussion about each one of these if it's not clear as I go over it. Okay, first one. All currents are equal. In a series circuit, like we talked about, all current through this particular circuit will be equal. The total resistance is greater than any one resistance. So maybe that's obvious, but the total resistance of all three components is going to be greater than any one resistance. Likewise, the total power is greater than any one component dissipation. So the total power dissipation of this circuit is going to be greater than any single one component. Larger resistance drops have higher voltage drops. Okay, now that may not be so obvious, but if we remember that voltage, remember we talked about what is voltage in terms of Ohm's law, and we said that voltage equaled I times R. Now remember that we have the same current flowing through this entire circuit, right? And so we'll say the current is going to be, we'll just show a flat arrow showing, or horizontal, meaning the flat relation, it doesn't change. Now, if the resistance goes up, then the voltage drop across that component will increase. And so We have three components here. This is the largest 30K, so this would have the largest voltage drop based upon the formula that current times resistance equals voltage, and since this has the largest resistance, all currents are equal, the drop here will be the largest. And finally, the last intuitive relationship, total voltage is greater than any one component voltage. So the total voltage in this case is 120 volts. This will be greater than the drop across any single voltage. And those are referred to as intuitive relationships about series circuits. Then mathematical relationships. In a series circuit, the following relationships exist with regard to current, voltage, and resistance. Now, the first one, and we have something here called IA. In this case, A has to do with applied current. So the current that is applied that comes out of our power supply is going to be equal to the current that goes through R1, R2, and R3. And that's kind of a given, but the current is equal through all components. And mathematically, that is what that states. Okay, resistance. The RT, in this case, the RT is the total current, or excuse me, the total resistance. So the total resistance of all components is going to equal, in this case, R1 plus R2 plus whatever, and the Rn just means is however many components there are. So the total resistance in this case equals R1 plus R2 plus R3. And VT for voltage, and again this is total voltage. Now the total voltage in this case is 120 volts, but it will equal the voltage drop across R1 plus R2 plus R3, and then V to the N again indicates however many voltage drops there are. The applied voltage in a closed loop is equal to the sum of the component voltage drops, and that's what this says right here. This important relationship is known as Kirchhoff's voltage law. Okay, polarity of voltage drops. When current flows through a resistor, there is a corresponding voltage drop across that resistor. The point where current enters the resistor is negative, and the end where current exits will be positive. So here we have our power supply. It is supplying current, and the current is flowing in this direction, and notice we're on the negative terminal here, but at the first point here where we enter a component, the polarity is going to be negative, and then the other side will be positive. And when we do our circuit simulations, you'll be able to go in with a voltmeter and measure this and confirm that that is in fact true. In fact, if you do some real circuits, you can measure them with a real voltmeter, and you can see that that is in fact the reality. So the polarity here would be minus the positive, minus the positive, minus the positive. And it kind of makes sense if you think about if you had a battery, and let's just pretend that we had just a single component. Say this is the component over here, and the battery is such a positive and negative that the polarity across the component would be just like that. The positive would be at the positive side, negative would be negative. At any rate, the point where current enters the component is going to be the negative side of the component. Now, closed loop equations. The following procedure can be used to produce a closed loop equation to describe a series circuit. And there are two steps in this. First one, label the polarity of voltage drops and sources. So here we've got the polarity, and we did this in the previous slide, but here positive to minus, and then minus to positive, minus to positive, minus to positive. Start at any point in the circuit and write the voltages indicating polarity as you progress around the loop in either direction. Remember, the polarity of the voltage drop is determined by the direction of current flow. Finally, move around the loop and write the voltages that are on the exit ends of the components. And so we could do this. We could start if we in fact, let's go to the next slide, and we'll do, there's a little more space on the next slide. And what we're actually doing is applying Kirchhoff's voltage law. And another way to state Kirchhoff's voltage law is that the algebraic sum of all the voltage drops and all the voltage sources in any closed loop equals 0. And you can do this by summing the polarity of each component based on where does current enter the component. And so if we look at this and we think, well, current is flowing in this direction, and we're going to evaluate the polarity based on where does current enter that specific component. And so if we start here, let's just start at this point right here. So the polarity where current enters the power supply is positive. So we start out with 120, and then we're going to sum, and we're going to base on where does current enter the component. So we start out here with a positive, and then we're entering this component, and we have a minus sign. So we go minus 60, and we continue around minus 40, continue around, and minus 20. Now if we sum these values, the sum is going to be 0. And that's what we were alluding to in the previous slide, that the sum of all the voltages around a circle are going to equal 0. And that is another way of stating Kirchhoff's law. And if you were a conventional flow person and you wanted to do it going the other direction, you could just as well do it, but you must be consistent when you do this. If we say that positive forces are moving in this direction, then we would start out at this point, and we would start out with negative 120 going this way, and then we would go plus 20, and this way plus 40, and then this way plus 60, but again our sum would be 0. Now I'm going to encourage you to read the text on this particular subject, and there are several circuit simulations that you can do in multi-sim to prove this, and you need to be able to go in with in the simulation and attach a multimeter and actually measure these drops and see for yourself that this is the way it is, and that Kirchhoff's voltage law does make sense. And if you algebraically sum all the values in a series circuit, the sum will be 0. So we've looked at Kirchhoff's voltage law here in solving a closed loop equation. We've looked at polarity of voltage drops. We looked at mathematical relationships. We looked at some intuitive relationships of series circuits, and we looked at what is a series circuit and what is not a series circuit. So this concludes our section on series circuits.